Good day everyone. Today we'll be talking about main memory in operating systems. I'm Clement Lim Jun Long and this will be for my subject operating system BIT 1213. Let's get into it. So what is main memory? Main memory. It is a part of a computer where data and programs currently in use are stored temporarily. It allows the CPU to quickly access and process information while the computer is running. When the computer is turned off, the data in main memory is lost. This is because the main memory, also known as RAM, is volatile. Let's look into the main memory in operating systems. There are several key roles of main memory in operating systems. Firstly, multitasking. The main memory supports this through holding multiple different active processes at the same time. The second, we have memory management. Operating system will use memory allocation strategies such as fixed or dynamic partitioning and paging and segmentation. Thirdly, we have virtual memory support. The operating system will utilize both the main memory and secondary memory to simulate more memory than available physically on our computer system. Fourth, you have program storage. It temporarily holds programs, both system and application software, while they are running in a computer system here. Let's move on to the benefits of main memory in an operating system. As shown right here, there are several key benefits of main memory in our operating systems. Firstly, for multitasking, it enables running multiple applications at once. It also maximizes CPU utilization through parallelism. Secondly, we have memory management. It ensures efficient use of memory resources, prevents memory leaks and fragmentation, as it also supports dynamic allocation based on process needs. Thirdly, we have virtual memory support. It allows execution of large applications even with limited RAM. It improves system flexibility and resource management. For the fourth one, we have program storage. It allows for quick access to programs without repeatedly loading from slow secondary storage, such as from a hard disk drive or our solid state drive (SSD). How does main memory work? For memory management, our main memory has two main memory management methods. The first one is swapping. As you can see here is the main memory and here is the secondary memory. In the main memory, we have operating system and we have user space. So the first process will be swapped in from the main memory here into the secondary memory here, as shown by this arrow and the process here. Meanwhile, the second process here in the secondary memory will be swapped into the main memory here to be used by the main memory. To utilize the main memory, the second process will utilize the main memory here, and the first process will be stored back into the secondary memory. This is how swapping works in basic terms. For memory management, there is also memory management techniques as shown by this diagram here. Let's look into this diagram. Memory management techniques will have two subcategories. First is uniprogramming and also multiprogramming. Under multiprogramming, there is two subcategories too. First is contiguous memory allocation. Let's look into contiguous memory allocation first. Under contiguous memory allocation, there will also be two subcategories. The first one is single contiguous memory, and the second is partition allocation. That is for contiguous memory allocation. As for non-contiguous memory allocation, there is also two subcategories here. There is page memory management and also segmented memory management for our non-contiguous memory allocation. That is for memory management techniques. So how does main memory work in tracking memory? First, For tracking memory, it will use a free list table. The OS keeps a list of empty addresses. When the program needs memory, the OS picks up some empty memory from the list and gives it to the program. When the program is done, the OS will return the memory back into the list for other programs. That is for free list table. The second one, we have bitmap table. Each drawer is marked with a 0, which represents free, or 1, which represents that it is in use. By drawer here, it is a free space. It is referring to a free space in our main memory, like a free partition, basically. For an example for the bitmap table, here we have 1, 1, 0, 0, 0, 1. This means the first two drawers are used as represented here by the two ones here. The next three are free, as represented by the three zeros here. And the last one is used, as represented by the 1 here. The OS looks at this map to decide where to put the new data. Continuing in tracking the memory here. The third one is page tables. Memory is divided into equal blocks called pages. Each program has a page table. It is like an address book that shows where its pages are stored in the memory. The OS also keeps a big list to show which pages are free and which pages are in use. So let's look at memory deallocation. Once a process is finished, the memory is deallocated in order to make space for other processes in the queue. In a fixed partition system, the memory blocks are simply set from busy to free once a process is done. In a dynamic partition system, there are multiple different algorithms used to deallocate memory. How does memory work? For memory deallocation in computers. A program requests memory when it needs to do something like store data. After it is done, the memory must be freed. If it is not freed, it causes memory leaks. This means unused memory is still marked as in use, which can slow down or crash the computer system. So let's look at joining free blocks. As for joining two free blocks, this is used when a process that was deallocated is next to another free block. The two blocks are then combined, taking on the address of the starting block which was deallocated. As you can see here, this one is busy, free, 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 free. Oh my god. I mean, process currently in use is next to a free block, as represented by this diagram here. The process is deallocated and is now free, as shown by this diagram here. The blocks are then combined and take on the address of the allocated block. As for joining three free blocks, it is used when the deallocated process is between two free blocks. They are combined into one free memory block. The entry for the memory block will have no address or memory block size. As shown by this diagram here, the process currently in use is in between two free blocks. As you can see here, this one is free, busy, free. Next, the process is deallocated and is now free, as represented in this diagram here. Next, the blocks are combined with no address, as represented by this null symbol here. Next is isolated block. It is used when the deallocated process is not near to any free blocks. The process will replace any null entries that exist in the list. The first step for this is the process currently in use is not next to any free blocks, as you can see here, busy, busy and null. The process is deallocated and is now free. As you can see here in this diagram, there's a free block and there's a free block, another free block, and there is a null block. Next, the process is moved into the previous null entry. This makes two blocks here. This creates two blocks here that are free. So that is for isolated block. So let's recap about the primary memory. Primary memory stores data and programs. It is capable of being accessed directly by the CPU. This allows for a faster rate. It improves efficiency by reducing access time. It also aids in reducing lag. Primary memory exists as either RAM or ROM. Let's look into RAM versus ROM. On the left here we have ROM, and on the right here we have RAM. ROM here stands for read-only memory, whereas RAM stands for random access memory. For ROM, it is non-volatile. This means that your information will be saved even when there is no power supplied to your computer system. However, as for RAM, it is volatile. This means that when there is no power supplied to your computer system, when the RAM has no power, the information stored on the RAM will be lost. For memory allocation refers to the process of reserving computer space for running programs and services on the computer. After the process ends, the memory used will be available again and can be used for other processes. There are two kinds of memory allocation: static memory allocation and dynamic memory allocation. Let's look into those two. On the left here we have static memory allocation, and on the right we have dynamic memory allocation. For static memory allocation, memory for the process is reserved by the operating system, which assigns the object a name used to access the block of memory. For dynamic memory allocation, a suitably sized block of memory is allocated by the operating system for the process, in order to reduce wasted memory in the main memory. For multi-programming system, memory allocation helps to prevent computer errors or crashes. Two memory management schemes are used by operating system: fixed partitioning and dynamic partitioning. For here we have fixed partitioning on the left and dynamic partitioning on the right. For fixed partitioning, it manages memory by dividing main memory into multiple fixed size partitions of equal or unequal size. This leads to fragmentation, which is unused space within each partition, which leads to wastage. For dynamic partitioning, it allocates the exact amount of memory the processor needs to optimize more free spaces. This allows memory to be used for other processes. It follows two algorithms to allocate memory: first fit memory allocation and best fit memory allocation. Here we compare the first fit memory allocation and best fit memory allocation. Here on the left we have first fit, and on the right we have best fit. For first fit, it searches through all available memory allocations, starting from the first block. However, on the best fit, it searches through all available memory allocations possible. For first fit, if the partition fits the process requirement, the process is allowed to the first block. However, on best fit, it allocates process to the smallest possible partition. On the first fit, it may lead to memory wastage, as processes with low memory requirements are allocated with partitions with higher memory. For best fit, it leads to least memory possible being wasted, but may take more time when making allocations. Next is delay recording. If memory needed for a process exceeds the available memory, the operating system shifts the current process onto secondary memory as virtual memory. When the process needs memory to operate again, the time taken to shift the process back leads to delay, which is mitigated with primary memory. However, main memory is capable of experiencing delays due to a variety of reasons. There are three main causes of delay in primary memory. The first one is limited bandwidth. When multiple cores of a processor try and use the main memory at the same time, it will lead to a bottleneck during high intensity usage. The second one is memory controller saturations. when the processor sends a large amount of requests to use the system in main memory. Next is cache misses. This is when the system must fetch the process from the main memory as requested. Data cannot be found in the cache. That's all for delays in primary memory. And here is our references. And that is all.